Oh my goodness.
Okay, so we're continuing on chapter. This one's actually short, so we'll start on chapter 6 soon. And then I did post an announcement. I'm sorry for my office hours. I had to do this little test because they thought I was exposed to COVID, even though I feel fine. But they said if you're vaccinated, you feel fine and wear a mask, you can come. But it was actually the state that notified me, not none of. But usually my schools will say, oh, you know, someone was in the same building as you, but don't worry about it. But this actually came from the state, and then they never tell you where you got exposed. So, but suppose I was exposed the 29th. Fine. Or I didn't know until yesterday. I'm like, why? Tell me now. So, but I've been fine. But I decided that I test myself at home and I'm negative, but I went ahead and had another test just to make sure. But I don't know. Kind of bummed because I think with that new vaccine, but they said I gotta wait. So, of course, they never show up when you want them to show. But let's do that now. So anyway, we'll continue chapter 5. Oh yeah, that's what I was gonna say. An announcement about when I open chapter 5. So it'll probably start Thursday, and then it'll be a week from Thursday. And then the quiz, you know, will start probably Thursday, most like 99%. Start Thursday and week Tuesday. Okay. And I renumbered the quiz because I somehow got ahead of myself. I numbered the quiz for work. So this is going to talk about Sanger and his sequencing. He got the Nobel Prize for sequencing proteins and nucleic acids. Super talented. So I'm going to answer questions. We went to graduate school. But Edmund came up with protein sequencing and enhance it. You know, there's always improvements like on your electronic devices and so forth. There's always updates. He uses compound PITC, and you can use that to sequentially sequence from the amino terminus onward up to a certain size, 50 amino acids. So the problem, it's great you can sequence up to 50 amino acids, but most proteins are bigger than 50 amino acids, so you have to use enzymes or other methods to cut up the proteins into pieces and then sequence them and then put them back together like a puzzle. And they actually did that for sequencing the genome, the same idea, even though that was DNA. They had to do sequencing and cut it up into pieces using dideoxy sequencing, which I think I am going to talk about at some point, and get the pieces together. And we don't draw the mechanisms for that, but it's shown here. So we have the chemical PITC, it attacks the amino terminus, and then it's cleaved from the amino terminus with acid, and then they can use chromatography based on what comes out of the chromatography. We talked about different types of chromatography. Affinity chromatography, not likely they're using that here, because they were using raw amino acids and want to be quick. So they can do it based on size, charge, or polarity. And so this one, what amino acid is that, by the way? They're the same. It's because you know. I heard some people say histidine, and that's histidine. So that should be histidine. Good. So as I mentioned, because most proteins are bigger than 50 amino acids, you do have to, they know some reagents or enzymes from others that can cut peptides into pieces and then they can put it back together. So they know trypsin cuts after lysine and arginine. And so we know what type of amino acids they are, right? What property they have. Polar, not polar, acidic or basic. Okay, they are polar and basic. Very good. Okay. Chymotrypsin cuts out tryptophan, tyrosine, and phenylalanine. So they all are aromatic, which is just a fancy way of saying, hey, we have a ring. Okay. A ring. Okay. Cyanogen bromide is a chemical that only cuts after methionine. That's like super specific. And then, now this is weird because all the other ones have names that are not an organism name, but then they decided to call this one after an organism, Staphylococcus aureus. It likes acidic amino acids. And then this is an example here, but unfortunately this example is all one letter abbreviations. You know how I feel about one letter abbreviations. Don't like them. Okay. But this is an example. So the idea is that sometimes they use multiple reagents to cut the proteins, and they know that they cut the peptide bond after a specific amino acid, and they get all these fragments, and it's like a puzzle. They have to get overlapping fragments to put them back. Do this, it's not going to be like alphabet soup up here. It'll be one letter abbreviation. So we can do this one. This one's not so bad. So we have to assume though they used Edmond degradation to sequence these little peptides after they were cut. Okay, so they already know that of that fragment and that's after the aromatic amino acids. Either the second one or the third one was the last fragment because leucine and serine are last. Okay. So we know that. Then we look at trypsin, it likes to put after lysine and arginine. But this one's kind of nice. You can flip a coin. Leucine and serine are last, right? So that's how the switch fragment here is last, the first and second one. So just with that information from the first two, we already know the protein starts with glycine as amino terminus. Yeah, the C terminus. But this, so then they have extra information or cyanogen bromide cuts after. Except that if it cuts after methionine, then the second fragment has to be first for methionine to be the last fragment, and it's tyrosine. So we already confirmed it already with the first three, but sometimes you need the fourth. Are there any questions about that one? It's more challenging. Pay attention to syllabus. 7 points. So they're probably. Yeah, so it's the same protein. Agents and got different fragment terms. And so the idea by doing more than one reagent to cut them, then they'll get overlapping fragments. But we were pretty lucky to actually figure it out. Well, the trypsin was pretty easy there, but it helped. So you really didn't need the cyanin, I can say that. The cyanogen bromide at this questions. multiple choice. So if I did it, I'd probably do multiple choice this time. So, but this one's not actually having you figure it out, it's telling you what it is. And we always assume by convention this existing. And then anything on the right side, like assume that. Can anyone tell me the exception when we don't assume that? I give you a hint, secondary structure, which secondary structure would not always be evident. Beta sheet, if it's anti-parallel, so correct, I shouldn't say right, I guess correct. So if one peptide beta sheet is amino terminus, C terminus, but it's anti-parallel to the next one. Never remember the anti-parallel beta sheet? Yes. That's the exception, but otherwise. So this one is asking you if time trips an end, what would the fragments be? Which one's the correct pattern if you use both? But you have to remember. Trypsin cuts out the lysine and arginine. So based on that, what fragments would we get? So if we look at this sequence here, well, it's going to cut out. It's going to cut out this arginine for sure. Tyrosine and phenylalanine. Which one? E as a dog. That makes cuts out the tyrosine. So the phenylalanine by itself, or does anyone think another one's better? I think that's good. You would think.
I'm sorry.
It has something to do with the carbon versus the nitrogen, but I'm yeah, I don't know if that's because the basic precedes that. That's a good. And sometimes you want to make peptides. Okay. You can see the protein. You want to deliver and cut up a protein for various defects. For for example, they could cut that up to make an antigen. That's not listed here, but it says drugs and stuff. It's also offset in culture to make the vaccine, or if not any vaccines. That's no one here. Do vaccines. And then how would you get these peptides? Purification from a tissue. We talked about grinding up tissue, getting the crude homogenate, using genetic engineering. Well, that means putting. You have to have the gene. You have to put in a plasmid and. Is it the expression vector? Expression vector is the protein. It's like if you want to prove out, see if someone may be exposed to a virus, but is it Just showing you how they can chemically make a protein. Purpose. Okay, and then they can do so they make sure that the carboxyl permanent one is open, but so if they want amino acid here on generic. Want the carboxyl group of this one interact with this one, they have to block the other residues. So it's a block it at the ends that they don't want, but the two that they want to access. And it reminds you where our peptide bonds are here. And, you know, they can make it. Or lines here, this one, when they say R20. On that, but we're just looking at what the benefits of it are. We're not machine where they analyze it and they show you which protein you get. But you don't get, you know, this, they don't let you get. So here is that 2D gel electrophoresis. Does any you're exploiting when you separate protein by 2D gel electrophoresis? Is that two techniques in one? Sizes, but it's SDS page, which separates by size. And then, so size of solution, size properties, which would be SDS page, and what's the other property? PI. So, I mean, you could do them separately, separate by chart. One does it all in one, but then it looks like one of those okay, and then you know where your protein is based on size. Now they didn't label the axes here based on size and isolation. It sounds fancy gel life, but you just got a piece of gel, that's all. It's not, they have to have a name for it all. Now, if you know how big your protein is, it's pretty big, you leave it. Since it is, what structure it may have. So it's like when you run an SDS page gel, you have a molecular weight standards, and then you compare it to where your protein is. So they have standards built into that computer so they know what the protein is. So alpha helix there is just alpha. So they can recognize it. X-ray crystallography and NMR structure determination. Okay. And you know, crystallography, you get grow crystals, okay, and depending on if they fract it, they can determine the shape. Used as an example, which is one formless. So it's good to start with the small one. map, and then they can build. Map. I think they're pretty. But yeah, so they can get their little protein model. Okay. It's not active, it's dead. It's sort of like when you do prepare a microscope. Micro. See it. They did extra. Which finds iron or, you know, and then you get nitrogen. Substrate of product. So it's not being bound by anything. So going back to NMR, the NMR looks at nuclear spins. Okay. So this is super small. Okay. In that mass spec again. Okay. And their sample, which again was 5 minutes. Okay. Okay. They can get the proteins. And this goes really in a lot of detail about. Then you don't have to crystallize it because then it's dead. Okay. But looks at a protein as if it can get. You'll see that in your protein project, they'll just have the small subunit. You've actually done it. And some people try to do organic chemistry. Organic. That's all I remember. Sure. So then we're going to go 6. Any questions? Keys to the last few quizzes. Sometimes you have to bug me because I forget, but that was good because then I did it for you. Chapter 6, this talks about protein. Favorite, one of my favorites. I always say that. How much RNA sequences except as comparisons are less stable, and the sugar is more reactive than DNA, but we haven't really talked about DNA. I mean RNA that much. And then we talk about amino acids, proteins, and then I pointed out as we're leaving last. Those practice problems to try. And then going to they do a lot of it, and like they do everything in this. Part two. Structure. Like make up this. Charge across the membranes, and it doesn't have to just be from outside to inside the cell. It can be to and from your favorite organelle. And then there's cell signaling, which we do towards the end of the body. Have many days on. Some are genomic caretakers. That's and so we have transfer proteins allowing ions in, and this enzymes, okay, which we'll discuss. This is citric acid cycle, electron transport, for example. We have structural proteins, myosin, microtubules, intermediate. Here it's showing you cell signaling. Look, signaling is always like a protein talking to protein talking to another protein, and finally, someone actually does. I don't know if you've ever been on hold and you call. Oh, just a minute, we'll get that person. Oh, okay, we'll get that person, and then it's like a few people later, you finally get response. Red blood cell signaling, like that. And then you have these genomic caretaker proteins. Some example are histones. They help package the DNA to allow RNA polymerase to do transcription. Others like to say, hey, slow down on the cell cycle. We have DNA damage. You need to fix it. You haven't copied over the DNA. Why are you going to mitosis? Okay, so they're supposed to be, those caretaker proteins are supposed to be looking out for us. But sometimes they get mutation or a virus interferes with them. So this is, well, we're not really studying malate dehydrogenase here to get the citric acid cycle. Let's convert malate to oxaloacetate as an oxidation reduction reaction is actually the helical. Generate used any So we'll be talking about myoglobin and today. Stores oxygen and makes oxygen more soluble, because of course we're mostly made out of water. Come out, they're like, yes, I can escape. And there, I'm a gas, not a liquid. Solubility of oxygen into water, and that's for aquatic mammals. Okay, that's the proof is that most of the room in your red blood cells. So much room that they get rid of the nucleus. Getting rid of the nucleus, you have hemoglobin. So like I just said, most of them should say red blood cells. But you probably, so the red blood cells pick up the oxygen in the lungs. But then later on, like carbonate. With one of them, we'll see that it only has tertiary level structure, whereas hemoglobin has quaternary level structure. Does anyone remember the difference? So R group interactions among one protein. One protein. Tertiary, and if it's multiple proteins or subunits, you can do it. Exciting. So myoglobin because it only goes up to tertiary. And remember, not all proteins go to quaternary. Hemoglobin has quaternary. But we're going to see that. So it's important to know that this heme group will form a corporate ring. I have to say heme group shorter, easier to spell. The hemoglobin and myoglobin as its cofactor. Cofactors help enzymes do their job, just like coenzymes help them do the job. Coenzymes are not enzymes, but of vitamin origin. Cofactors are usually metal ions, but in any case, they help them do their job. Even though you have amino acids with different side groups, and there's 20 side groups, there's only some side groups that are reactive and help them. They don't contribute, whereas histidine, lysine, and arginine, or aspartic acid, so they can help with acid-base contaminants. Okay. You can temporarily do covalent bonds with another cysteine if that's needed. They're only showing me 4 out of the 6 ligand side binds. It's only showing atoms in the ring themselves bind. We'll also see there's a nitrogen is going to bind to it. So the nitrogen and the histidine ring. Hemoglobin or myoglobin. gonna be not a night. Acidic group is advanced. To the protein. Okay. For coenzyme, we call it co-substrate, which means it doesn't stay permanently attached. It might go back and it's bound to malate. Very dehydrogenase. It's permanently bound enzyme versus if they say co-substrate, then it can come back and forth. Showing you the E group. There's green, but that depends on the text. But we don't have and then it's got 4 nitrogens in there. Doing this figure, it's hard to see the proximity, which actually binds. It's used Greek letters in science or alpha beta. Secondary structure. Because as you can see here, it's all alpha helical, but they have alpha 1 and 2 subunits and beta 1 and beta 2 subunits. So beta 1 and beta 2 subunits are not beta sheet. The alpha subunits from the beta subunits, they have some amino acid sequences different. I know years ago someone was arguing with me. I asked if it was all alpha helical, all beta sheet, and mixed them out. And they said, well, it's both because it's called alpha beta. Picture, so. Now I'm not logged into smart where people watch this regulation. I'm sure I'm not. Knowing me, I'm pretty good. So there's no point with the animation. So this is looking at the finally we have the heme group over here. Right here, they made a little bit, they look tiny. Surrounded by those 4 nitrogens in the heme group. And from that histidine is the proximal. Very slow dashes there. It can enter. That's bound there. It's bound there. Because they would probably have these. histidine wasn't there. And basically, let's go by 250 times greater. Okay. The histidine is there, and makes it more uncomfortable. But without that, there 250,000. Okay. So this is comparing with and without oxygen in terms of which is attached to the rest of the protein. You see more of these changes, more obvious changes in hemoglobin because it's usually proteins with plotted there that have a structure and show change. Okay. So here we have okay, there's the histidine. This histidine is the proximal one. The proximal histidine is the one that touches the iron, not the distal one. That just prevents carbon monoxide poisoning. Okay, so that proximal histidine is there. It's attached to the iron, but there's no oxygen here. But notice it's bent, meaning the iron is not in the plane of the heme ring. We need the oxygen to pull it into the plane. So when oxygen is present, it's in the plane of the ring. But of course, the iron is attached to the proximal histidine, so it's not shown very well in this figure. But everything moves. So the oxygen is going to pull the iron into the plane of the ring, which is going to pull the proximal histidine closer and move that alveolus. So this picture doesn't show it, but it does it at an angle. It doesn't do it straight. But because the oxygen allows it to be plane. X-ray crystallography people like to use the term T and R. But tense is the T state and R is a relaxed state, but it's kind of confusing, especially with hemoglobin. In the tense state, hemoglobin is not binding oxygen, but the relaxed state is doing its job in binding oxygen. To me, that's the opposite of what I would think. If you relax, you're not doing that. But anyway, here they did color in the 4 subunits. This is the deoxygenated state versus T and R. So that way you know what it's doing. Otherwise, you have to remember T. It's to me tense, like I'm working. Sorry, very hungry. A certain molecule binds there to regulate how or slowly oxygen binds the hemoglobin. Okay, this is the oxygenated hemoglobin. Smaller, okay, and that excludes a molecule that was sitting here preventing oxygen from binding. So they do have 2 distinct structures, whether you have oxygen bound or not. So they use even though it's static, and sometimes they use X-ray crystallography for presence or absence. But main thing here, we're going to see that here, what they're looking at sliding of the protein subunits. Its locations of aspartic acids and aspartic acid and tyrosine is indicated. Okay. Now, when oxygen is bound, we're going to, and different R groups are going to interact with each other, but the strongest bond, so they're not going to be breaking those. So we're breaking non-covalent bonds. Or like when you separate DNA strands, they're separating, they're not covalent bonds, but bound. Now instead of this type, because aspartic acid and the tyrosine are too far away from each other. Shape enough, they're slid past each other. Shown is between alpha 1 and it's a concerted versus, and so we're looking at high hemoglobin and all their stuff. They're playing at the same time, together all at once. So in that idea, the subunits should be changing all at the same time from deoxygenated to oxygen. They should and then you are, and then you are, and then you are. So sequential means one after another. Okay, so it's a little slower. Sort of like both. It doesn't like presto, the oxygen binds and I'm going to bind them all. It actually has some resistance, as we showed on the previous slide. Those hydrogen bonds have to slide. So initially there is resistance, so it's like sequential. So one binds, and not everyone binds at once. Then there's a chain that allows all the others to bind. So it's like a combination. One binds, breaks the hydrogen bonds, and then the other three can bind. It's actually a combination. So in a way, initially it's sequential, but once we get over that barrier, breaking the hydrogen bonds, then it is concerted. The other three are like grab the oxygen. You just have to break the first bond. Like I tell my other students, if you want your friends to come into your house, you have to open the door. Saturation is the percent of hemoglobin in your mouth. So the denominator would be all hemoglobin. All the hemoglobin in the cell, whether it's bound by oxygen or not, would be in the denominator. The numerator would just be oxygenated hemoglobin. The fraction is what fraction, or if you did percent, you multiply by 100, what percent of hemoglobin has oxygen bound versus the total. They're making it generic here, but basically when you talk about PL, that's protein bound to its ligand or small molecule, in this case, hemoglobin bound to oxygen. Protein not bound to oxygen, so bound. In the numerator, protein bound by ligand. In the case of hemoglobin, myoglobin would be oxygen. So what percent of oxygen or hemoglobin is bound by Now, some people leave it as a decimal, and some people multiply it by 100. And when we get to this chapter, I did put practice problems. You see this from Dr. Bates. Otherwise, I have not known. So that's all. It sounds fancy. We use the symbol sign, but others use the letter. The y is on the y-axis, and you're like, are they being redundant? We know that's the y-axis, but they're talking about fractional saturation. It's simple saturation. I mean, fractional saturation instead of this Greek letter. Also, they talk about Kd, which is a dissociative constant. This signaling. Receptor has a high affinity for its ligand, for its hormone, binding to the receptor. So Kd is the ratio of dissociated associated. And remember, Ka's, it's been a while. Ka, and that was H plus times A minus over the protonated acid. Same thing. We just changed the symbol. Why they changed it, but they did. Same idea. So if you understand Ka, you have three separated from each other or associated. And usually the bigger the number, associated or dissociated. Is it dissociated with the D? Yes, okay, good. Dissociated with the D. The smaller, meaning they're associated, so they have a stronger interaction. So if you're comparing different proteins and KDs, the ones with the smart KD bind their substrate readily at low concentrations, or bind their ligand or their hormone at low concentrations, or oxygen at low concentrations. These are different fractional saturation tells you what percent are bound. This tells you how tight the association is. Smaller number, stronger the interaction at low concentration. Questions? How are we doing? It won't be so muffled. I like a microphone. Next time, but just to start another way, I remember what it's like. Sometimes I forget that I always think about it. Myoglobin, compare myoglobin. Like if you look at an atmosphere or pascals. Fractional saturation looks like it almost is like totally like vertical. It grabs it like that, like a rocket ship. It's saturated with oxygen, can't bind anymore. Before it can get up there, and eventually can get up to full saturation like that one, but it's more S-shaped or sigmoidal. It takes those subunits have to talk to each other. Sequential model, where the first oxygen has to bind there, hydrogen bonds broken. Once those hydrogen bonds, it's super easy for the other three oxygens to have the concerted model.
slow, only one oxygen shift that those hydrogen bond interactions. Oh, we can all bind now. That oxygen helped us out, and now it's easier for defining. To bind at low concentration. It's hemoglobin in the tissues because it's like it won't goes in that well when the oxygen concentration is low because it's supposed to deliver it. Whereas myoglobin is like you can see that the low concentration is bound to it. It's like I'm not giving it enough. I don't care if it's on delivery person inside of it. Whereas hemoglobin is like, oh, they're low in oxygen, I better deliver it. We can look at it the reverse way. I'm not doing that. Not anytime soon. So we'll continue this on